Alright everybody, welcome to a new segment or series of segments that will discuss the exact equations. Alright, now let me be honest, so far when I did the autonomous or separable, because autonomous is separable, right? So separable approach as well as I did the linear approach, it was not too bad, right? You were okay. Right now this is a point where it's gonna get a little bit more complicated, right? And the next segments, the next set of segments that I'm gonna focus on will be substitution. It will be similar to this in terms of the difficulty. I just want to warn you that things are getting a bit real, alright? Let me start by defining what a differential is. You did cover this in your calculus course. Differential of a function. Okay? I am not focusing my efforts into my particular class, but let's say that I have a function and these are, let's say that there's an n number of independent variables that expresses the behavior of a depending variable, right? And now what I'm going to do is I'm going to add, or rather write you what the differential of this particular function would be. Del f, del x1, dx1, plus del f, del x2, dx2, plus del f, del x3, dx3. I shouldn't have written the third one. I think the point was clear. But anyways, del f, del xn, dxn, right? That will be what I have here, okay? Why do I have a differential in here? Why partial sign? Why not regular derivative sign? Well, because, hey, when I take a partial, that what it means is I'm looking at how it changes in the x1 with respect to x1, but I keep all the rest of these independent parameters constant. That's what it symbolizes, right? So that's why you have yourself a partial sign over here, okay? So this is, so far, I didn't do anything about the differential equations course. I just explained to you what a differential of a function from your calculus courses are. And right now I'm gonna do this. In a typical differential equation course, the first order ODE, I don't have to, but I typically have two variables. One is independent, one is the dependent variable, right? So I'm gonna customize this equation for that reason. And the way that I'm gonna write is this: z will be equal to f x comma y. Okay, let me explain. See, z, I call this y. The confusion is, I have a y here, but I'll do my best. So this x1 is I call x, x2 is I call y, right? So basically, these are just arbitrary letters from the alphabet. So there's nothing unique about these. I can do whatever I want, right? I can call it A, B, C, D. So now I have my z, and this is x1, this is x2. If I take a look at this equation, you will see that this will be like this: dz will be equal to del f, del x, dx, plus del f, del y, dy, right? That will be the differential of a two-variable function. Okay, so now this looks like a differential equation. Because remember I talked about the differential form in the first module, and this looks like this, there is something over here, there's something over there. I call this m, I call this n over there in the first module, if you remember that. And now it's coming back to me. Okay, so now this looks like a differential equation, and this is dz. So if I take the integral of both sides, what you will obtain is, obviously I'm going to get myself z for the left hand side. Well, let's say call it plus c as well to be consistent. And then I need to evaluate the integral of the right hand side. Okay, del f del x dx plus del f del y dy. Now the question in here is, how am I going to achieve the right hand side? I will discuss that in a couple minutes. All right. Well, why don't I, give you a flavor of what's going on over here? Let me do this. Let's say that I'm being asked to find this. Giving you a differential equation to solve in an exam setting, in a homework setting, or some other setting, right? And here's what's going on. So how am I going to solve this? Would be the question. Is this separable? No, not really, right? Is this linear? I don't think so. So now let's look at whether this is whether this equation can be approached from this concept that we do. And let me give you a hint, and let me write the final answer for you. In reality, here's what it's going to be. The c will be equal to x squared minus 5xy plus y cubed. Okay, this will be the solution of it. Okay, so now let me take a moment over here and take a look at it. I said that this is f. Basically, this is f. Del f del x. So I need to get del f del x and I need to get del f del y, right? So del f del x will be 2x minus 5y, you see it, right? And let's look at del f del y while we are here. That's going to be minus 5x minus plus 3y squared. Do you see something in here? This is that, this is that. Yep. So it really is the solution then. Okay, the solution of this function or differential equation is this. So now, I don't know about you, but I have two questions myself. I said that, hey, this worked, right? I have a solution. Question number one. How do we know that I have the exact differential over here? This is called exact differential. How do we know I have a different exact differential? Because I may not have. Let me give you another example. X squared minus y squared dx plus x squared minus 2xy dy is equal to 0. You know, I will show you how to approach this, but this is not an exact differential. So you cannot simply take a look at the way it looks and say that, you know what, the approach is going to be exact. So I have to have a very specific methodology or criteria to ensure that this is an exact differential. That's the first question I want to answer. Okay. The second question I want to answer is, okay, now I know that this is an exact differential. How am I going to find it? Okay, how am I going to find it? So those are two questions that I have in my mind. I don't know you, but from my side, right? So let me start by answering the first of these questions. Okay. And how do I know whether there's a, how do I know that this equation cannot be solved with this approach, but this can be solved? How do I know that? Let's look into that. And I'll write the theorem. It's kind of fast. So here's what the theorem says. Del m del y if is equal to del n del x. This is an exact differential. And in here, here's what we call by m. Here's what we call by n. So let's write this here. M xy dx plus n xy dy is equal to 0. That's what the differential equation is. So in this particular case, obviously this is del f del x. This is del f del y. So this is what I need to check. And let me do a very quick proof that this kind of makes sense. Let's look at the del y. What is m? M is del f del x. Is it really equal to del x? What is n? That is del f del y. So look here what's going on over here. The top side is the same. The bottom side is kind of switched. So now the question is it really matter whether I have a function, I take the partial of it with respect to y first then x versus first with x then y? Will it really change the final answer? If this was a class setting face-to-face, unfortunately I hear this more often than I would like to. Students just say yes, it does matter. But that's not the right answer. Okay, it doesn't really matter. It's again coming from calculus. Differentiation, the order of the differentiation doesn't really matter, right? At the end of the day, I'll get the same answer. So this will be satisfied, as long as this is okay. All right. So that's why I need to check this. Okay, this is what I need to check. And now I answered the question number one, for all of us. And I said that, hey, this doesn't exist, right? Why don't I demonstrate that? Whatever is in front of it is called n. Whatever in front of it is the other one is called n. So now let's look at del m del y. Is it really equal to del n del x? So del m del y. So that's going to be del y of x squared minus y squared. Will it be really equal to del x of n? And n is x squared minus 2xy. So what this happens is I get myself minus 2y over here, and over here I get myself 2x minus 2y. You clearly see that they are not the same, right? So now I will not be able to use this approach for this particular question. Okay. By the way, there is something, I didn't teach you that yet, but this equation can be solved by separation of variables, right? We'll cover that approach as well, so you will see how to solve this particular question. But this is not an exact question, okay? All right, so let me give you a flavor of the second question that I asked you, all right? So let's go here. So let's say that this information was supplied to me, all right? And this will be, let's write it in here, this will be del f del x This is m. And this is n, which is del f del y. So what I'm going to do is the approach is going to look like this. I will take, I'll start by this. So then I move this del x to this side, take the integral of both sides, so I get myself an f. And then I will go to the second equation, because there, you will see that there will be an unknown in that equation, and I will just plug that value back in here, and as unknown, I will be able to understand what the final form of the equation is. If this was not clear, which is, I speak really, I covered this quite fast, the best thing to do here is to illustrate with an example, and that will be the next segment you will see very soon. Okay, once I cover that, everything will be crystal clear, hopefully. I'll see you soon. Take care.